All right, let's get right into it. Welcome, everyone. To all the vocational students and future master techs tuning into this explainer, I am absolutely thrilled to have you here. Today, we're going to talk about a topic that literally separates the true diagnostic masters from the parts changers. We are going to save you from the dreaded parts canon by mastering the underlying foundation of the modern engine management system. We're talking about identifying VREF circuit faults. For this explainer, here's our roadmap. We'll build the VREF foundation, dive into shared circuits and chaos, validate ground integrity, map out a diagnostic workflow, and finally, tackle advanced failures and heat. Okay, let's do this.
Part 1, the Vref Foundation. Let's decode that 5-volt baseline that essentially runs the entire engine management system.
Picture this shop floor nightmare scenario. A car rolls into your bay, it's stuck in limp mode, the engine is running terribly, and the dashboard is lit up like a Christmas tree. You plug in your scan tool, and you see 5 completely different engine sensors all reporting failure at exactly the same time. No way 5 sensors just died simultaneously, right? Why does this happen? Well, it really challenges us to think beyond individual components and look at the shared electrical environment they live in.
So, what is VREF? VREF, or reference voltage, is a stable, regulated 5-volt DC supply generated internally right there in the engine control unit. You see, sensors measure physical conditions, like pressure or temperature, but they don't produce electrical energy on their own. They absolutely cannot measure these physical conditions without this constant baseline voltage provided by the ECM. They're literally blind without it.
We need to draw a hard line right now on what components actually live in this diagnostic bucket. On one side, we have your VREF-dependent sensors, things like your manifold absolute pressure, throttle position, and engine coolant temperature sensors. These are completely reliant on that 5-volt baseline. But on the flip side, we have self-generating sensors, like your oxygen sensors. O2 sensors generate their own voltage through a chemical reaction. They do not rely on the 5-volt reference. So if an O2 sensor fails, that's an entirely different diagnostic path.
Moving on to Part 2, shared circuits and chaos. Let's look at how the ECU distributes this voltage and what happens when that distribution network goes haywire.
Think of a 3-wire sensor exactly like a simple light dimmer switch in your house. It's essentially a voltage divider. It takes that fixed 5-volt reference coming in, acts as a variable resistor based on what it's physically measuring, and then sends a modified signal voltage back to the ECU, usually somewhere between 0.5 and 4.5 volts. The ECU reads that return voltage and calculates the exact engine condition. But here's the kicker. Multiple sensors share that exact same 5-volt feed. And that brings us to the one shared fault principle. Under normal operation, the map, TPS, and ECT all have a clean 5 volts available, so the ECU gets accurate data. But let's say the map sensor develops an internal short to ground. It drags the available voltage down for every single shared device on that ECU branch. Now your TPS and ECT are only getting, say, 3.8 volts. They're going to instantly return skewed signals, and the ECU, it just sees system-wide chaos.
So the absolutely crucial point here is how you interpret the fault codes when this happens. If you pull dedicated VREF codes like P0641, P0651, or P0698, you must diagnose the shared circuit. Those codes mean an entire 5-volt bank, like bank A, B, or C, has failed. If you see those popping up alongside individual out-of-range codes like a P0107, do not chase the individual sensors. You have to attack the VREF circuit first.
Part 3, validating sensor ground integrity. Now this is the second most common trap for young technicians. Assuming a perfect 5-volt reference means the circuit is completely healthy.
0.1 volts. Seriously, burn this number into your memory. This is your maximum allowable sensor ground offset limit. It is a hard and fast rule for your electrical diagnostic testing.
Because here's the thing. Even if you measure a flawless 5.0 volts on your reference wire, it is totally useless if the sensor ground is poor. The ECU reads the signal voltage as the difference between the signal wire and the sensor ground. So if there's a bad connection creating ground resistance above 0.1 volts, it acts like a false voltage. A sensor that should be returning 1.0 volt might suddenly return 1.3 volts purely because the ground reference shifted. Your fuel trims and engine timing will react to a completely false reality, and you'll just be chasing ghosts all day.
Part 4. Diagnostic Isolation Workflow. This is the hands-on, step-by-step procedure to actually pinpoint these shorts out on the shop floor.
Before you even pick up a wrench, you must consult your OEM wiring diagrams. This is non-negotiable. Modern ECMs have multiple Vref output circuits to isolate critical sensors. You need to map out the exact Vref bank assignments, A, B, or C, and figure out exactly which sensors share that suspect 5-volt branch. Once you have your hit list, hook up a scan tool to monitor those reference voltage banks in live data.
Okay, here is your step-by-step workflow. Step 1. Leave everything connected and backprobe the Vref wire at an easily accessible sensor using a quality multimeter. Step 2. Verify the voltage is out of spec, meaning it's being pulled down below 4.90 volts. Step 3. Systematically unplug the sensors on that specific Vref bank one by one. Leave the Vref wire connected to the ECM while you do this. Step 4. Watch your multimeter or scan tool. You are waiting for the exact moment the voltage instantly recovers back up to 5.0 volts.
Let's see how this plays out in a real diagnosis. Say in our initial state, the circuit is pulled low to 4.10 volts. We unplug the TPS. Still 4.10 volts. We unplug the ECT. Still 4.10 volts. But the second we unplug the map sensor, bam! The shared Vref instantly springs back to health at 5.02 volts. Boom! You just found your shorted component, and you didn't fire a single part from the parts cannon.
Finally, Part 5, Advanced Failures and Heat. Let's cover the extreme edge cases that truly separate a parts changer from a master diagnostic technician.
Sometimes you unplug everything and the voltage is still wrong. Is it the wiring harness or is the ECU itself cooked? Well, here's a little advanced trick. Connect a 1 kilo-ohm resistor between the Vref line and ground. This is crucial. That 1 kilo-ohm resistor safely draws a very light 5 milliamp load. If the Vref collapses under this tiny load, the ECU's internal regulator is too weak. That points to an ECU fault. But if the Vref holds steady at 5 volts, the ECU is perfectly healthy, and your fault is a short somewhere in the downstream wiring.
Now, what if the voltage is actually too high? High Vref readings, we're talking anything above 5.10 volts, are rare, but they are incredibly severe. This is usually caused by an internal ECU voltage regulator failure that's drifting upward, or a wiring harness that has somehow shorted to a 12-volt source. This is a dangerous condition, guys, because it can permanently damage every sensitive component on that shared circuit. Most 5-volt sensors are simply not built to survive anything above 5.5 volts.
And then, oh man, we have the hot soak diagnostic nightmare. The ECU's internal regulator is very temperature sensitive. When the engine is cold, Vref is perfectly stable at 5.0 volts. But as the car warms up and engine bay temperatures creep past 85 degrees Celsius, that extreme heat causes the internal regulator to drift. Vref drops intermittently, the car runs horribly, you get codes, but by the time the car actually cools down enough for you to test it in the bay, the 5 volts are back and the problem has completely vanished. For these sneaky ones, you absolutely must monitor live data during a full, hot drive cycle.
Look, this is the absolute core ethos of a master technician right here. Always diagnose the circuit before changing parts. Multiple sensor codes usually mean one electrical fault. If you pull a code and immediately replace the sensor without performing isolation testing, you're just wasting your customer's time and money. The sensor didn't fail, it was just trying to operate in a broken electrical environment.
Which brings us to the end of our explainer. I want to leave you all with a provocative thought. If a single shorted wire inside a single sensor can literally take down an entire engine management system by corrupting the shared Vref, what other hidden electrical relationships are you missing in your day-to-day diagnostics? Always look for the shared systems, trust your foundational testing, and please put away the parts cannon. Keep learning, keep digging deep into those diagrams, and I'll catch you in the next one.